This video adds some more details to the way models work in QL. In the last video, we started with this symbolization key. We worked out that this was the corresponding model. The model is enough to tell us the truth value of any sentence containing these predicates and constants. We can figure out whether a sentence is true or false without worrying about what English language phrases were in the symbolization key and without having to know any geography. For example, I see is true in the model because the referent of C is in the extension of I. What if our symbolization key had also included a relation, a two-place predicate, like S? Here, SXY means X is smaller than Y. It turns out this is a bit more complicated. We know that the University of Discourse contains Crete, Manhattan, and Oahu. Here are the geographical facts. Manhattan is the smallest at 85 square kilometers. Oahu is second. Crete is the largest. So what is the extension of S? It might be tempting to write down the members of the Universe of Discourse in order from smallest to largest. That doesn't work though, so I put an X over it. The set containing Manhattan, Oahu, and Crete is just an unordered collection of things. If you wrote down that set, you'd just be repeating the Universe of Discourse. You'd be writing it in a different order, but it's the same set. In order to make the complete thought out of is smaller than, we need two things. Something to fill in the first blank and something to fill in the second blank. So the extension of S needs to be pairs of things, not just a set of individuals, but a set of pairs, where the first thing in the pair is smaller than the second thing in the pair. For this, we'll want another mathematical notion. An ordered pair is two objects in a specific order. We write it with angle brackets. Bracket thing 1, comma, thing 2, close bracket, is an ordered pair that puts thing 1 before thing 2. So the extension of S is a set containing pairs of things. The pairs Manhattan, comma, Oahu, Manhattan, comma, Crete, and Oahu, comma, Crete. Those pairs are the pairs of objects from the Universe of Discourse where the first is smaller than the second. That is, the two-place predicate S applies to pairs of things, specifically these three pairs of things. Although we constructed the model based on a symbolization key, we don't need to think about the meanings in English anymore. Once we specify the model, like I've got it here on the screen, that's enough to tell us whether sentences of QL are true or false, just in the way the assignment of ones or zeros to the atomic sentences was enough to calculate the truth value of sentences in SL. Consider this sentence. Parenthesis UC or UM, close parenthesis, biconditional SMC. We can determine the value of the atomic formula by consulting the model. UC gets a 0 because the referent of C is not in the extension of U. UM gets a 1 because the referent of M is in the extension of U. SMC gets a 1 because the pair of the referent of M followed by the referent of C is in the extension of S. The rest is like working out a truth table. The whole sentence gets a value of 1. It's true in the model. What about a sentence like for all x, not fx? Now, maybe you can guess this one just by looking at it, but let's take it step by step. To determine the truth value of a quantified sentence, imagine taking every member of the Universe of Discourse one at a time and plugging it in for the variable. What I mean is that for all x, not fx, is true in a model if and only if not f blank is satisfied for every member of the Universe of Discourse. If we plug in every member of the Universe of Discourse to that blank one at a time, the result is something that gets a 1. With this model, there are three objects in the universe of discourse. So for all x covers three possible cases. For all x not fx means not f Crete, not f Manhattan, not f Oahu. And if we look at f Crete, Crete is not in the extension of f. So f Crete gets a value of 0. That 0 isn't a truth value exactly, because Crete is an object rather than a symbol of QL. F Crete isn't a sentence, but we can still treat it as a 1 or a 0. And we can apply connectives in the usual way. The negation of a 0 is a 1. Similar reasoning applies for Manhattan and Oahu. We got a 1 for all three of these. That is, we got a 1 for everything that's in the universe of discourse. And that means for all x not fx gets a 1. It's satisfied in every possible substitution. All of them got 1s, so the universal quantifier for all x gets a value of 1. And since that's a sentence, that 1 means that the sentence is true. Now consider an existentially quantified sentence, like exists x, sx, c. Now, this existential sentence is true in a model if and only if we can substitute at least something, at least one member of the universe of discourse, and satisfy the formula. So exists x, sx, c is true in a model if and only if s blank c is satisfied. It gets a value of 1 for at least one member of the universe of discourse. And again, in this model, there are three possible cases. We get S Crete C, S Manhattan C, S Oahu C. The referent of C is Crete, so we look up the pair Crete, comma, Crete, and check to see if it's in the extension of S. It's not in there, so S Crete C gets a value of 0. The pair Manhattan Crete is in the extension of S, so S Manhattan C gets a value of 1. We could go on and check S Oahu C as well, but we don't need to. The important point is that the exists X says that we can find at least one thing in the universe of discourse that will satisfy the subformula. And we've already found one thing, Manhattan. S Manhattan C got a value of 1. So exists X, Sx, C also gets a value of 1, and it's true. Although longer sentences are more complicated, these strategies are enough to let you determine the truth value of any sentence given a model. A model is a formal structure. Even though the universe of discourse in this model is a set of 3 islands, it could be 3 of anything. For example, we could let the universe of discourse be the set containing the numbers 3, 4, and 5. Then we'd specify extensions and reference in terms of that UD. Here are the two models we've just looked at, side by side. I feel like I'm trying to pack too much onto the screen with this slide, so feel free to step back in the video if you have trouble seeing the details. By looking at these two models, I've labeled them model number 1 and model number 2, you can see they have the same structure. For example, everywhere Crete appears in model number 1, the number 3 appears in model number 2. And that means that sentences of QL get the same truth values in the two models. Just by writing down sentences of QL, there's no way to specify whether the sentences are about islands or about numbers. If you aren't sure about this, try out some sentences of QL and evaluate their truth in model 1. Then evaluate their truth in model 2. You'll get the same answer. These models have the same formal structure, so they deliver all the same truth values for the sentences of QL. Here's a summary of the key features of models. In QL, the structure that specifies the truth value of a sentence is a model. A model specifies a universe of discourse, an extension for every predicate, and a referent for every constant. The universe of discourse is a non-empty set. The extension of a one-place predicate is the set containing the things from the universe of discourse to which the predicate applies. The extension can be the empty set if the predicate doesn't apply to anything in the universe of discourse. It can be part of the universe of discourse if it applies to some but not all of the things. Or the extension can be the entire universe of discourse if it applies to everything in the UD. The extension of a two-place predicate is a set of ordered pairs. That is, it's the things from the universe of discourse that stand in the relation. And because the two-place predicate takes two objects, it has two blanks to fill in, it takes pairs rather than individuals. The referent of a constant is a member of the universe of discourse. It's the one member that's named by that constant. So in QL, the structure that specifies the truth value of sentences is a model. And that's the key idea of the formal semantics for QL. The notion of what a world is like is represented in QL by a model. It's a way things can be. It's what it is that makes sentences true.